There are three types of jet ignition. Active, like the one we're seeing, and was announced by Mahle back in 2019. Theoretically, it was ready for standard cars, but the fact is, no one ever used it. The semi-active, used by Formula One, and the passive, used by the Maserati V6, and now featured in the Jeep Grand Cherokee, that, with just a 4-cylinder 2.0-liter turbo engine, produces 324 horsepower. But which one is better? What are the differences? Let's begin. In the quest to reduce pollution and increase power, the first step was a single big injector, which replaced the carburetors and could adjust the fuel based on the weather and other factors. Then came multi-point fuel injection, which had one injector per cylinder. These injectors are located just before the valve, and now allow the fuel dose to be adjusted according to the specific requirements of each cylinder. Then the evolution continued, and currently, almost all turbocharged cars have direct injection, which involves placing an injector in the cylinder head to get the fuel directly into the combustion chamber. This process reduces the temperature, since by introducing the fuel in the cylinder, its evaporation absorbs heat. It also allows for stratified injection, maximizing power and reducing emissions under certain conditions. Although indirect injection is better under other driving conditions, ideally both injectors should be installed simultaneously. Regarding the spark plug, it remained practically the same. Materials like iridium began to be used. More electrodes were added. Power and control increased with individual coils, and multi-spark ignition was introduced in case the first spark failed. Among other things, more spark plugs were used per cylinder so that combustion would start from two places at once and burn everything faster. Combustion isn't an instantaneous explosion. Instead, it has a flame front that propagates at a limited speed. Initially, this speed was 15 meters per second, and thanks to the design of turbulent chambers, where the air is continuously mixed, it increases to 40 meters per second, same as 100 miles per hour or 160 kilometers an hour. However, at 5,000 RPM, the time to burn all the fuel is less than 2 milliseconds. Any fuel not reached by the flame front within that time will produce almost no thrust. In other words, the piston will already be too low and will contribute very little power. F1 engines spin at over 10,000 RPM, and the time to burn everything is less than half a millisecond, which aggravates the situation. In 2014, the regulations changed, and the amount of fuel per second that could be injected into the engine was limited to 100 kilograms per hour, or its equivalent of 37 milliliters per second. And the tank could not carry more than 35 gallons or 135 liters for the entire race without refueling. With fuel restrictions in place, raw engine power is no longer the deciding factor. With so little fuel, the 1.6 turbo engine couldn't handle it, and the conventional Otto cycle was abandoned in favor of the Miller cycle. While the piston is still moving down, the intake valve closes earlier, drawing in less air and thus maintaining the 14:1 air-fuel ratio. Furthermore, because there is more expansion compared to the compression stroke, there is an increase in efficiency and fuel economy. Generally speaking, the power output is obviously lower because less air and fuel are absorbed, but this smaller amount of fuel expands more, ultimately resulting in the savings we're looking for. To put it in numbers, it produces 10% less power, but saves 25% in fuel, so we come out ahead. The second problem was that F1 engines spin at over 10,000 RPM, and the time to burn everything off is less than half a millisecond. This process had to be accelerated somehow. Instead of using the advancing flame front to burn the mixture, we can use a small capsule with holes. Combustion occurs normally here, but now a lot of pressure is generated. Finally, this pressure expels directed bursts of flame, reaching distant areas faster. Now, the flame front advances and burns everything. This injection makes the equivalent flame speed greater than 60 meters per second, higher than the previous 40 meters per second. This development of Formula One resulted in 3 jet ignition systems: active, semi-active, and passive. The active is promoted by Mahle. This new technology still maintains one injector in its conventional position, but now incorporates another new mini injector right next to the spark plug. These two now operate within a pre-chamber, which, upon injecting a small dose of fuel and firing the spark, causes the combustion to be ejected through very small holes in the pre-chamber, forming these directed, very rapid flames. By burning all the fuel in the cylinder much more quickly, the result is like delaying the timing, but with the benefits of if we were advancing it. This reduces knocking by 20%, and more power is achieved. It also allows for higher cylinder compression ratios and increased turbo boost pressures without engine knocking. High-octane fuel is not required. This can result in much higher power gains and reduced consumption. The formation of polluting gases, such as nitrous oxide, is drastically reduced. Now, how much of the total fuel comes out through the normal injector, and how much through the small one? 3% of fuel is injected into the small pre-chamber, where, upon entering, it expels almost all the air, leaving the engine in an ultra-rich air-fuel ratio. It's almost as if the engine were choked. This also improves the hypothetical cold start. Then, the flames come out and ignite the remaining 97% of the fuel supplied by the other injector. Now, if fuel savings are desired, the main cylinder can operate with an ultra-lean AFR, as the flares take care of igniting the mixture. With the conventional ignition method, if too little fuel and too much air are supplied, the mixture will not ignite and the engine will misfire. It is estimated that with this ignition system, mass-produced vehicles will have the same efficiency as diesel engines, achieving the same low fuel consumption, but with significantly fewer emissions. They will reach 50% thermal efficiency. This means that 50% of the fuel burned will go to the wheels to propel the vehicle, while the remaining 50% will be released as heat through the radiator and exhaust pipe. We just saw the active jet ignition system that Mahle offers for regular cars. The drawback is that it requires an extra injector per cylinder. That is, one in the pre-chamber and another in the cylinder, plus the port injector. This would give a total of 3 fuel injectors. Also consider another high-pressure fuel pump and hoses. As we can see, this active system is the best, but it is very expensive. Formula One has a regulatory limitation that requires only 1 spark and injector per cylinder. Therefore, they cannot use the active system offered by Mahle for cars, and instead they use what is called the semi-active system, where the original injector has a smaller orifice to spray a small amount of fuel into the pre-chamber through a receiving hole. The spark plug then ignites this 3% of the fuel to form the ignition jets that will then ignite the rest. As we can see, this semi-active system requires an extremely special injector, with a dedicated orifice that could even open before the other remaining holes, which would be 2 injectors in one. This method might be even more expensive than the active method and less efficient, but it's the only solution to the regulation. And finally, we move on to the passive system. The Maserati Nettuno MC20 is not a conventional car. It is a supercar, and in 2020, it was the first to use this system. Now, in 2026, Stellantis' Hurricane 2.0 turbo engine, currently producing 272 horsepower, will have a new variant with turbulent jet ignition, boosting its output to 320 horsepower. This new engine will be fitted to the Jeep Grand Cherokee. Therefore, we could say that this technology is now in mass production cars. How does the passive system work? The pre-chamber does not have a fuel injector. In fact, it only has the spark plug. And the direct injector doesn't aim as well as the one in Formula One. This pre-chamber is fed by the normal engine process. That is, when it compresses, the fuel mixture enters the pre-chamber, and when it ignites, the jets are fired. The thing is, when the engine is running under low load, there is very little mixture in the cylinder, and it doesn't get into the pre-chamber, so the ignition doesn't work. So a second spark plug is installed on the side of the cylinder to work during this low load condition. In other words, 70% of the time, the pre-chamber is almost useless, because you rarely go full throttle. Basically, there's always someone ahead limiting your speed. Now, when you floor it, the cylinder fills completely and the pre-chamber works, effectively accelerating combustion. Basically, this is when the engine is running at high RPMs, and we need the fastest possible combustion. With this, the 272 horsepower Hurricane engine now allows for a substantial increase in turbo pressure, a 12-to-1 compression ratio, accelerated combustion, and a power boost to 320 horsepower. All this while also utilizing the Miller cycle, thus saving fuel. The injector operates at a pressure of 350 bar or 5,000 psi. Interesting, isn't it? One advantage of this system is that it's not very expensive. It uses the pre-chamber design and only requires an inexpensive additional spark plug. No special injectors or anything like that are needed. And for the power it delivers, it's totally worth it. This would also allow for a 20% engine downsizing. Instead of a 2.4-liter engine to achieve this power, you'd have a 2.0-liter, which ultimately saves fuel. Although there are some disadvantages. The small holes in the pre-chamber limit the exhaust of burnt gases, as well as the entry of new ones, which could be prone to failure. The combustion that occurs in this pre-chamber could fill the holes with carbon to the point of clogging them prematurely and causing everything to stop working. The system is only effective under high engine load. This passive system does not improve cold start as the active one. It does not allow lean AFR operation. It uses 2 spark plugs, and Formula 1 regulation forbids it. In the past, diesel vehicles had pre-chamber systems that worked at 400 bar, but they were discontinued due to improvements in direct electronic injection that today works at 2000 bar. I don't think that diesel pre-chambers will be back since diesel ignites as soon as it touches the air in the cylinder, and direct injection is faster than getting out of a pre-chamber. Today's most advanced gasoline direct injection system operates at approximately 350 bar, similar to the diesel pre-chamber. Honda also had the CCVC system in the 1970s, which was entirely carbureted. As you can see, it had an additional valve to access the pre-chamber. This pre-chamber was fed with a rich mixture, which then ignited a lean mixture entering through the intake valve. The result was lower emissions. Later, electronic fuel injection replaced all of this. However, with new emissions regulations, it's likely that the pre-chamber will be needed again with the help of electronic fuel injection. In summary, we have active system, uses at least 2 injectors in pre-chamber. It's the best system, but it's the most expensive, and nobody uses it yet. It should be considered that these additional injectors require a new high-pressure fuel pump, more hoses, more space, greater design complexity, and ultimately higher costs. Semi-active system. It's only used in Formula 1 due to regulations that allow only 1 injector and 1 spark plug. The injector is a double injector and shoots a special jet into the pre-chamber, which is why it's called semi-active. Finally, the passive one has a normal injector, but since fuel does not always enter the pre-chamber at low load, it must use a second spark plug to ensure operation. This system is low cost, but effective. When do you think the active system with its full potential could come into use? Do you think it's a good idea for Formula 1 to limit the amount of fuel to improve engine efficiency, the quantity of injectors or spark plugs? Or do you think they should be beast machines that scream and put on a show? Leave it in the comments, and don't forget to leave a like and subscribe. I have more 3D interesting videos to watch.